Thanks, Chris, for inviting me to talk about CI, which is Stevens Institute for Artificial Intelligence, and I'd like to welcome everybody today to this conference and the talk. Stevens Institute for Artificial Intelligence kind of is a culmination of our realization that we've been working on artificial intelligence in different aspects of this at Stevens for a while now, and so it just made sense for us to come together and make an organization that would concentrate all the efforts in one place. So before I go on to that, there's a quick note about me. I have about 15 years of experience with AI and ML myself, working on different aspects of AI and ML on different problem spaces, ranging from wireless communications to steganography, steg analysis, so a bunch of cybersecurity type problems, and so on and so forth. Recently, I was named a Jefferson Science Fellow, which gave me the opportunity to work at the Department of State here in the US as a science and technology advisor to the Department of State, where my primary responsibility was to defend the US positions and in technology policy in international fora. But I also participated in what's known as interagency processes, where we talk to the Department of Defense, Transportation, NSF, everybody, on key interests on things like Internet of Things, 5G, wireless, and so on, as well as AI, ML. And I was on the US Department of State Machine Learning and Artificial Intelligence Committee, which was focused on AI, ML applications, very specific to the Department of State's needs. I have, of course, served as editorial boards of several IEEE conferences and journals. I am the founding chair of the IEEE ComSoc's TCC and special interests on security. Funding is from the usual NSF, AFRL, NIJ, and other sources, as well as industry. And I've been named recently as an NJI HOF Innovator Awardee. So the CI, Stevens Institute for Artificial Intelligence, was founded officially in March of this year. And we are now over 40 faculty that have been working on artificial intelligence problems in a very diverse set of spaces, hence the name of institute instead of a center. We do span all the 4 academic units of Stevens, which is the School of Engineering and Science, Systems and Enterprises, School of Business, and the CAL. CI focuses on interdisciplinary research. So we came together as a team more with the focus of being able to break these boundaries and stop working in our silos so that we can actually start looking at problems that might be of interest that cross these traditional boundaries. The faculty involved in this institute are funded by NSF, NIH, DoD, work with industry, have been supported by foundations. There are professional recognitions, including National Academy of Engineer members, Jefferson Science Fellow, NSF Career Awardees, NSF Center Directors, and so on and so forth. The vision of CI is to explore opportunities to advance AI and machine learning to serve humanity and to improve disciplines such as healthcare, business operations, the workplace, and the education. So it is a very diverse set of application areas, but then that is the nature of AI. So if you have seen Gartner's hype chart, which they publish every year, which I'm sure you've looked at, it goes like this usually, and they have different technology marked along this curve, where things that are just beginning to catch up, things that are reaching the hype level, things that have just matured and started to be deployed in real life situations. And various aspects of AI fall along this entire curve. And if you look at some of the reports that comes from McKinsey, you can see that AI pretty much impacts the entire spectrum of what you would call your day-to-day life. So it's no wonder that we here have a very wide set of interests in AI. So the faculty in CI have coalesced around 9 different areas that we have expertise in, from healthcare and biomed, fintech, cybersecurity, foundations of AI and ML, societal impact, art and music, cognitive networking and computing, robotics, perception, and human-machine interaction, environment, and energy. So the names you can see associated with each of these bubbles are the faculty that are coordinating the efforts in these various areas. I will be going on to present some examples of the work. It is by no means exhaustive, and we really would not have the time to go into all the details. But this hopefully will give you an idea of the kind of problems that we work on. So the first example I'm taking here is from the healthcare and biomed cluster. So what we work on here is non-invasive detection of early stage Alzheimer's disease. So Alzheimer's disease is one of the very fast rising diseases today, with a lot of interest in trying to come up with new modalities in treating it, in trying to diagnose it, and so on and so forth. But it is one of the most challenging diseases in the sense that it's very hard to catch it in early stages. So, and catching it in early stages is important because you can plan ahead for the kind of lifestyle that you might have to change because of this. So and usually in a primary care physician setting, there is not enough time for the doctor to actually evaluate this person, unless there is a need to do that, unless the person actually says, okay, I would like to be evaluated for it. And the early stage detection, which is called the mild cognitive impairment stage, conventional methods are only as good as 59% accurate. And to do that, you need to use biomarkers, things like fMRI scans, which are very expensive. Each scan is about $5,000 or so. And you would need a continuous monitoring of that. So this work here uses the person's way of using language, the way they speak, the way they type, the way they write, to catch this potential mild cognitive impairment. So we use the choice of words, the grammar, the concept ordering, character preference, and so on and so forth, use certain NLP techniques, natural language processing techniques, as a precursor to the processing, apply some AI and ML work on it to figure out whether the person has MCI or not. And we can get up to 85% accuracy in detecting early stage Alzheimer's. The neat thing about this is that you can implement this algorithm in a thing like Alexa or your phone, so that the Siri with which you interact will be able to catch it as time goes by. And you can imagine a situation where this thing can trigger a notification to your physician, and someone can contact you and say, why don't you just book an appointment, come in for a formal testing. So we looked, in the previous case, what we did was look at NLP as a tool. It's just one part of the tool that goes into that big engine. Here it's the opposite of that. We are using natural language generation to do some work in fintech, where one of our faculty works on generating a summary report based on things that are client revenues, client interactions, client trades, mind of the market, and so on. Here they use deep learning algorithms for natural language generation, which is the sort of an inverse problem, if you like, from NLP, to generate a report that would look something like that. So there is also other work going on in the fintech area, where there are some faculty who've been looking at SEC filings and trying to find if there is a fraud going on there, some detection of intent to deceive in the unstructured reports. So there are different aspects of, I'm just trying to highlight with these two examples how different aspects of the inverse problems of each other can be used in very different areas. Here is an example of from the cluster of cognitive computing and networking. Here, there is a scenario where you've got one of your vehicles, automated vehicles, which have to talk to the base stations and the edge servers, mainly to exchange information. And the idea here is how can you, as you go on these autonomous vehicles and autonomous infrastructure as well, you are looking at problems where you need to coordinate between these vehicles. You can coordinate between these vehicles to have a better traffic flow. So the problem here is, with every device that you have on your mobile, they are all equipped with multiple radio access technologies. So if you take your cell phone, you have Wi-Fi, you have your cell phone. That's at least 2. And you can get more than that. You can get more different types of cell phone connectivities in there. When you have a bunch of data or a bunch of applications that you want to run on your phone, and you want to do this in a smart way, when you have power constraints, because your phones are usually running out of charge, what are the best ways in which you can transfer the data that you need to transfer between all these different radio access technologies? And what is the percentage of data you would put on all of these? This is not a static problem, because if you had a very well set understanding of Wi-Fi is good and LTE is what it is, you can solve this problem one shot. You have your optimal solution, you put it in and you're done. But that's not how it generally works. You have a whole bunch of dynamically varying situations. Low latency sensing and adaptive decision making is important when you're doing connected cars. Things have to happen at very quick speeds, especially to accommodate the movement, the mobility of the vehicle, as well as the person's reaction time. There are predicting and tracking wireless channel conditions. It's very easy to. It's fairly easy. It's a well-studied problem if you already have a good understanding of what the wireless conditions are now. But if you want to predict it, and if you want to see a few seconds out from now, that's a harder problem, and you need to use AI/ML techniques on that. So there's a whole bunch of other problems that you can study. Here is another example of cognitive computing. And in this case, we are talking about edge networks and mobile devices, a very similar scenario, but a different problem. Here you have an app that's running on your phone, and that little, that one there is the way the app is broken down into smaller programs. Usually each thing has a component. These components interact with each other. And when you want to make this app run in the most efficient way, what does that mean? It usually means use the smallest amount of battery power, use the minimum storage, use your Wi-Fi/LTE interfaces intelligently so that you're not driving up costs, actual money cost, as well as cost in transmit power and so on. So here you want your solution to be automated, in the sense that each mobile device cannot do this on its own for the entire landscape. So the solution is usually cloud-based and is sent in to the mobile. This is one setup where you would be using reinforcement learning and so on and so forth to figure out all the different moving parts of this problem. In the cybersecurity cluster, faculty are working on privacy-preserving deep learning. So this is an extremely important question nowadays, especially with all the European laws on the right to be forgotten and so on and so forth. We have a challenge now where it is evident that getting all this data from different aspects of people's lives and synthesizing information from that is crucial. But we want to make sure that when you're crunching all these numbers, the identity of the person whose data you're actually taking is not accidentally leaked. So how can you access data, even if it is the kind of data where you're removing all the names and obvious identifying factors? There are still ways in which you can infer who this person really is. For example, if you take a sample of salary studies in a company, and then you start ranking them in different ranks, like so, a certain stream of faculty, for instance, are making X amount of money. This is the highest, this is the lowest. And then if it turns out that at the topmost level there are like 3 faculty, and you give out a number for that, it's very quick to zero in on who that person is. In fact, there's been research that shows that you can actually find the SS number of people if you're not careful, even when all of these was removed. You can find that out if you don't take certain precautionary measures. So privacy preserving data mining and privacy preserving deep learning is a tool where you consciously design these algorithms so that there's no accidental leak of information about the person. Another work here is to, we all know about that machine learning computations are often outsourced. You put it in clouds, you put it in various places where you don't really control the machines, and you have no idea who's looking at it. So the goal here is to verify that the machine learning results returned by the cloud are the same as you would expect, the honest, real answer. So another faculty is working on causality. We all know about the caveat between correlation and causality. If you keep looking for correlation, you'll find correlation in practically unrelated data. It doesn't mean causality. So this faculty is working on understanding causality between different data streams. So just because heart health risk increases when blood sugar is higher or a person has diabetes, is it actually related? We know now that it is. But is one caused by the other? So these kind of problems. So she works on methods for learning causal structures from challenging observational data, early risk factors for heart failure, mechanisms behind brain swelling, links between exercise and hyperglycemia, using mobile data, so things that you can collect from Fitbits and so on. In the robotics cluster, there is actually, this slide is very busy because there's a lot of projects here highlighted. As you can see, there is a lot of wearable robotic systems in this picture. The one where the child is running is a pedi shoe, which is instrumented sandals for clinical gait assessment. Here you have a safe, which is basically an ankle-foot electromechanical orthosis device. There's a pelvis hip tracking system, which measures it's basically good for injury and rehab work. And robotics and human-robot interaction, there is some faculty are working on not just marine robotics, they're also working on land robotics, but I just put in one of the examples here, where they make perception and learning and decision-making with sonar-equipped, remotely operated vehicles. So when you want to map the bottom of the ocean in really murky condition, and you're not going in down there, so it's an ROV that maps this thing, and you use learning and decision making to plan the path of this robot so it doesn't get stuck. The one on the right hand side is about robot and human interaction. So there's a lot of work that's been done in robots and path planning. What's the optimal path the robot should take to do whatever task it is trying to do? Most of that work is about doing that in very laboratory settings, where whoever is working with that robot knows that there is a robot, and they adjust accordingly. But if you want that robot to actually work in real life situation, it's going to be out there, say in the mall. People start to interact with that. People start to see the robot, and they start to move differently. So they start to avoid it. They start to go circle around it. So things like that are being studied currently here to do crowd control in disaster situations. So if I put a robot in certain places, will people's paths of movement change so that we can have a better exit strategy from a building that's in a disaster zone, for example. So this is about motion planning methods for mobile robots in socially normative behaviors. Those are, again, very few of the projects that we are working on. There are a few brochures that I brought in, which I've left outside, that have a few more examples, and there are a few more examples in the website, which we hope to keep updating as we go. So at CI, we welcome collaborations with the rest of the world to basically, like we said, we are looking to solve bigger problems that tend to be solved better if people from different disciplines come together. One of the mechanisms for collaboration would be the industry affiliates program, which we are working the details on, and it has a very similar structure to what the SAIL is doing, where you can have access to faculty and research teams and PhDs, sponsor PhDs, and so on and so forth. We're also looking at university and foundation partnership to solve problems that are more of interest to humanity, things that are a cure for something difficult or a more social economic problems. We have started running what we call the summer immersion program. For now, it's for undergraduate students, where we get these students here for 6 weeks. They follow a research lab. They work with the research students. They get hands-on experience with the problems that we're working on. And they get a tour, of course, of the campus and see what else they're able to do. We are planning on extending this to high school students as well in the near future. Conversations are on for MS and other educational programs, which are, we already have a whole bunch of master's certificates and master's degree programs in AI. They are currently offered by ECE department, by the CS department, by the business school. So there are lots of different master's programs in AI. What we are trying to work here is a different one, which is very application oriented, where there would be a core course component that comes from the basics of whatever it is that drives AI, so the foundational aspects of AI and ML. But we'll have a very practical angle where the student can choose to go in any one of those 9 clusters for a deeper dive on different aspects of AI and its application areas. We are working with NJ vocational schools to help them understand the impact of AI on the curricula going forward, because vocational schools are worried about there is a general mass panic in certain areas that AI is going to be disruptive in not the good way. So to try and get that understanding better articulated is one of the goals of that interaction. We are also working with the Life Sciences Talent Development Network here in New Jersey. They are focused on developing career pathways for new workers, as well as what you'd call the working poor. Their idea is retooling all of these workers so that they can be ready for AI and AI's impact on life sciences, which spans everything, including healthcare, and get back into the stream of the economy. So we are working on developing a curriculum that is not going to be fixed for any one university. It's actually going to be all of New Jersey, so that anyone can adopt that curriculum and become a pathway. So the university, like Stevens, can work with any university or any other entity to let this thing happen, which will, and the key thing there is that we are identifying pain points in the industry focused on life sciences. So these are pretty much the main things going on with the CI, and we'd welcome your collaboration.